So here we are dealing with a cogeneration system. Okay, the Rankine cycle operates with the steam which is entering the turbine at state 1 of these conditions, 55 bar and 370 degrees Celsius. So that's state 1. The condenser pressure, right? This is the condenser here. The condenser pressure is 12.4 bar. The isentropic efficiency of the turbine is given. Okay, the energy which is rejected by the condensing steam is actually transferred to a separate process stream of water which is entering at 1 megapascal and 120 degrees Celsius. So this water is entering as compressed liquid, and it exits as saturated vapor at, of course, the same pressure. So we are not rejecting the heat to the environment, we are rejecting the heat in a heat exchanger to another process stream of water. Okay, that enters at, that is operating at a different pressure. So this is certainly a non-contact type of heat exchanger, right? We are having two streams at two different pressures, and it comes in at lower temperature and exits as a saturated vapor at a slightly higher temperature, the Tsat. Okay. Now for this specific problem, we need to do a couple of things. We need to first determine the mass flow rate for the working fluid. The working fluid is the water here, but here we're talking about the working fluid within the cycle, right? And if the mass flow rate of the process stream, which again is water, but it's the process stream, right? It's the thing that's going in here, is 22,700. So this mass flow rate is given, m dot p is given. We need to calculate mass flow rate of the cycle. Okay, this is the first thing. The second thing that we need to do is we need to devise and evaluate the exergetic efficiency for this overall system. Okay, the overall cogeneration system where you're providing work output plus some heat output. Okay, so this is what we want to do. Now, before we go ahead and solve for mass flow rates or anything, or even the exergetic efficiency, in all these sort of problems, we need to sort of define the states and get the values of enthalpy and entropy. Okay, and that's what we will do first. So this is how the TS diagram looks like. Here we are having 2s and 2 simply because the exergetic, the isentropic efficiency is mentioned. Okay, so the process, the expansion within the turbine is not isentropic, although the compression within the pump is isentropic, right? Because there's nothing mentioned about the isentropic efficiency of the pump. Okay, so now let's very quickly look at how we get the enthalpies and entropies at all the different states. We have done this before, so I'm going to go rather quickly. Any questions? Feel free to stop me. So state 1 is easy. We have the pressures and temperatures, get it from the superheated vapor table. For state 2, we got to make use of the isentropic efficiency. Okay, so first of all, what you do for state 2 is you determine the enthalpy at state 2s. And the way to determine enthalpy at state 2s is pretty straightforward. You have the pressure, and we have the entropy as well. S2s is equal to S1, right? That's what happens in an isentropic process. Now, using this value of S2s, you determine the quality of the mixture S2s, and using that you determine the enthalpy H2s. Okay, now this is what you have. This is what we have done before as well. Now you have S2s, you have H1, and you have the isentropic efficiency given, right? And again, to remind you, the isentropic efficiency for a turbine is simply the actual work output divided by the ideal work output, okay, or the isentropic work output. So we have everything known here. The only thing that's unknown is S2. So you plug in the numbers and S2 comes out to be 2,838. And if you recall, we mentioned that the enthalpy that comes out here, S2, is always greater than S2s, right? So that's what you see is the case here as well. And I mean, it makes so it's a quick sanity check to ensure that you're doing the correct calculation and you're putting the things in the right order. OK. So why does S2 have to be greater? Well, the work output is smaller, right? The actual work output is smaller. Sorry. So, OK, we have state 1, state 2, and state 3 is very straightforward. State 3 is simply saturated liquid. Nothing is mentioned, but you know, it's you can assume the exit of the condenser would be saturated liquid. So you don't have to bother anything. You already have the condenser pressures, so you get what's needed. State 4, well, to determine the enthalpy, again, we got to make use of the pressure difference between state 4 and state 3, and also the specific volume at state 3, right? So it's an incompressible liquid. We've already discussed how to do this. We make use of this reversible work input formula. Now, we need to go to state 5 and state 6, right? We have determined the 4 states for the working fluid. Now for this other process stream, it comes in at a pressure of 10 bar at a temperature of 120 degrees Celsius. Now from the table, we know that this is compressed liquid phase. And for compressed liquid phase, well, we discussed that it does not, the properties such as enthalpy, they don't depend on the pressure so much. They depend on the temperature, all right? So all you need to do is get the value of HF at this value at T5 of 120, and you get the enthalpy at that. We also would want to do the same thing for the entropy. We're going to make use of the entropy here. Okay. State 6 is again straightforward. You know the pressure, you know the quality. Okay, the quality is given as saturated vapor, pick up the numbers, straightforward. So this is how you build the table. Now, the real work starts after you have built the table, right? In the exam, when this, or even in the classes, if I give you this sort of a question, I'm not going to ask you to determine all the properties in the table. I may give something easy, maybe to determine enthalpy for state 1. Then I may give something like maybe to determine enthalpy at state 2 and maybe state 4, right? Just to make sure that you understand how to do the stuff. But you'll be spending a majority of the time in also looking at how to make use of it. Okay, so the first thing is we need to determine the mass flow rate of the working fluid within the cycle. Okay, so any ideas? How do we determine that mass flow rate? We have the mass flow rate of the process stream. We are having heat exchange from this, the heat loss during the process 2 to 3 is the heat gained during the process 5 to 6. Okay, that's all what we are having within the heat exchanger. So how do we get the mass flow rate of this working cycle, or the mass flow rate that's going here from 2 to 3?
Energy balance or mass balance?
Yep, energy balance. We don't do mass balance here because the mass is remaining same in both of the cycles, but excellent. The answer to this question most of the times is energy balance, right? And when the masses are changing, you take mass balance as well. Thank you, Abdul Malik. So you just have to put energy balance here, right? So whatever, so you can put the energy balance in either way. You can just write it as the energy lost by the hot fluid is equal to the energy gained by the cold fluid, or you could also write it as, summation of MIHI is equal to summation of MEHE, meaning the mass flow rate and the enthalpy coming in has to be equal to the mass flow rate and the enthalpy going out. There are two inlets at state 2 with the mass flow rate of m dot cycle, and state 5 with the mass flow rate of the process stream, which is given, right? Either way, you end up with the same equation, same energy balance equation. And here we have the values for all these enthalpies, H2 to H6, right? We also have the mass flow rate of the process stream, m dot p. The only thing we don't have is the mass flow rate of the cycle. Once you plug in the numbers, this is what you get. Okay, so 2.5 to 10 power 4 kilogram per hour. It's a reasonably high mass flow rate, but sort of smaller than the flow rate that we were looking at in previous examples. So this is as simple as that, right? It's a very simple problem testing your concept of applying the energy balance. And this is again, as I mentioned before, these are the sort of questions that you can expect, right? I mean, questions which test one concept at a time. All right. This is done. So now let's look at the second part, which is to evaluate the exergetic efficiency for this overall system. Okay, so till now we have been looking at the exergetic efficiency for the compressor, for a pump, for a turbine, and so on. We have not looked at the exergetic efficiency for the entire system. Okay, so so the way we solve it is pretty similar, as we'll find out in the next few minutes. So you just have to basically remember the exergetic efficiency formula, right? I mean, the exergetic efficiency is simply desired output by required input. And here you got to be careful in figuring out what is the output, what is the input, and everything needs to be written in terms of exergy changes, right? And you get the exergy changes from simply the exergy balance equation that you have. All right, so here we're not looking for each component, we're looking for the entire cycle. Okay, so when you look at the entire cogeneration system, the desired output that you're getting here is the network output that we obtain from the turbine plus the exergy transfer that's happening to the process stream, right, which is happening here in this heat exchanger or in the condenser. Now, for this desired output, which consists of two different things, work plus heat transfer, we need to provide some input. And the input is simply the exergy increase within the boiler, right? We need to heat up the fluid. So that's the simple exergy input that we are providing. All right, sorry. So coming back to this, I mean, we certainly expect there to be some difference between the exergy input and the overall exergy output, simply because there will be some irreversibilities. Okay, and that is what is the exergy destruction. So the question is, what is the exergetic efficiency here for this case, right? How high is that? So here we just need to write the net rate of exergy output, which we said is coming from the network output of the cycle, plus the exergy increase of the cold fluid. Okay, so we got to be careful to make use of the exergy for the process stream and not use the sorry, the exergy decrease of the hot stream, because those two values could be different. Okay, energy balance and energy works out, but the exergy is not balanced. So you got to be careful about when you're using this. Same way, we just have to write in terms of the input, is just the exergy input to the cycle, right? Exergy input that's happening within the boiler between stage 1 to 4. Now, the work input, the net work output of the cycle, it's simply turbine work minus pump work, and it's something that you can easily determine, right? We have all the four enthalpies, we have the mass flow rate of the cycle, so it comes out to be pretty easily in this manner. Okay. Now, the other thing that we need is the change in exergies. Now, the change in exergies are also easy to determine once you have the enthalpies and the entropies. All right, and we picked up these entropies directly from the table. So we have the enthalpies and entropies for all the four states, just a matter of plugging in the numbers in this formula, and you get the exergy changes for both the process stream here and for the working fluid here. Okay, so once you plug in the numbers, you got to be careful to make use the correct mass flow rates. Okay, this is the mass flow rate of the process stream. This is the mass flow rate of the working fluid. Okay, once you make use of this of the correct mass flow rates, correct changes in exergy, the exergetic efficiency comes out to be 92% almost, right? It's pretty high, and it's simply very high because we're making use of it of the almost all the exergy available, right? There is some amount of exergy destruction, but I mean, from an energy balance point of view,